This is your.
That works.
Yes, it's already on. Okay, so our last speaker of today is Oskar Vafek, and the title of his talk is Symmetry, Maximally Localized Wannier States in Low Energy Model for the Twisted Bilayer Graphene and Narrow Bands.
Okay, well, thank you very much, especially to the organizers for the kind invitation and opportunity to speak here. This topic is very much related to the previous talk, and hopefully it will give answers to some of the questions that were raised. The work was done at the National High Magnetic Field Lab in Florida State, and it was supported by NSF. My collaborator on this is Jian Kang, who is a postdoc at the Magnet Lab. The relevant publication is on the archive, and it will show up in print soon. Okay, Luke has already nicely introduced the system, but let me just walk you through this. Imagine that you have two graphene monolayers sitting on top of each other, and then you twist, let's say, the top one relative to the bottom one by an angle theta. You will get a new pattern, which is superimposed on top of the original honeycomb pattern, the so-called moire pattern, that introduces a new wavelength into the problem, which is, for small angles, much larger than the interatomic carbon spacing. And now this new potential that you create will then reconstruct the electronic waves from the two graphene layers, and therefore fold the band structure, and in principle can give you new interesting effects, such as flat bands, as was pointed out in the previous talk. Okay, so I'll come back to this in just a second, but that's the playground now. Of course, while this has existed before, this field has received an incredible sort of impetus during the announcement at the March meeting by the MIT group of Pablo Jarillo Herrero, in which they discussed what has been discussed in the previous talk, namely that for special angles, range of angles near the so-called magic angles, the system, when doped near the neutrality point, which is marked by 0 here, can exhibit either insulation, and if you dope away from this insulator, a superconductivity, and if you dope too far from it, you lose the superconductivity, and you actually have a metal. What's remarkable about this is that this does not happen in a monolayer. It does not happen in the AB stacked bilayer, as far as we know. It seems to be intrinsic to this special moire system. Now, as Luke has nicely explained, there are several features in this experiment which are worth discussing. So this carrier concentration doesn't, over here and over here, where you have an insulator, doesn't correspond to anything special in a monolayer graphene. This arises entirely because of the reconstruction of the electronic waves due to this moire pattern. So this is the emergent aspect of it, although this is a single body effect. On the other hand, what happens halfway between this band gap here and the neutrality point, namely the insulator here and the insulator here, is believed to be driven by electron-electron correlations. And of course, superconductivity is also driven by electron-electron correlations. Okay, now let's see. So how should one think about this? Well, imagine at first that you start by decoupling the two graphene monolayers. So there's no interlayer hopping for just a second. Then all you have is just two copies of graphene, the top and the bottom layer. And each one of them is going to have a Brillouin zone. Let's say the top one is marked by the blue and the bottom is marked by the red, but because they are twisted relative to each other, the Dirac points, the corners of the Brillouin zone, fold into slightly different points in this so-called mini Brillouin zone, which is the Brillouin zone you get if you have a commensurate angle and get the new periodicity due to the moire lattice. And so if you were to count the Dirac cones, well, each monolayer, each graphene monolayer has two of them, the K and K prime, which is equivalent to this one. And this one you see folds over here. So you get two Dirac cones from the top layer that would fold into two different points in the mini Brillouin zone. And then two other Dirac cones from the bottom layer, which fold onto also the corner of the moire Brillouin zone. So if there was no coupling between the two layers, what you would expect is to see two copies of the Dirac cone at each one of the corners of the moire Brillouin zone. And so clearly we are dealing with at least four states that we need to worry about. Now, this is a picture from the band structure that was solved by tie binding calculation in the original paper by the MIT group for the commensurate twist angle that is the closest commensurate angle to the so-called magic angle that they measure. And what you see is that in addition to just having the four cones, which are now these points in the corners of the mini Brillouin zone, there's also band reconstruction away from the Dirac points, namely in the center of this Brillouin zone. And that can give rise to band gaps. Now in this particular case, the band structure calculation actually does not reproduce a band gap on the bottom of the band, where we know experimentally there is a band gap there. It does reproduce a gap at the top of the band. That's an excellent question. The monolayer graphene does not have particle symmetry to begin with. And so in this specific calculation, you have nearest neighbor hopping within a layer, you have a next nearest neighbor within a layer, etc., etc. And those hoppings, although they do drop, they don't drop completely to zero. All right. So now there are other calculations in which you relax the structure a bit, and this gap can actually be achieved in a microscopic calculation. Okay, so basically what's going on in this experiment, presumably, is that you start with something like this. Imagine there's a band gap here. And then you start filling it by field effect transistor. Down here, you see you would have an insulator. You start going through the neutrality point, which would be over here. There, we actually do not have an insulator, although there is, as Luke pointed out, there's a drop in the conductance, but it doesn't go to zero. So these two bands are actually not separated from each other. And then if you continue, you will then deplete this, and that would be this band gap. Okay, and this field hasn't entirely sorted out the magnitude of these band gaps. Experimentally, they're known to be about 35, maybe 40 MeV. They come out smaller in the band structure calculations, but nevertheless, these band gaps here are understood to be essentially non-interacting physics. The interesting effects are over here. Now, all right. So we were motivated by this, and as many other people, we wanted to understand what would be the correlated electron physics in the, I should also mention what the notation should be. So you see, this corresponds to quarter filling of this entire band structure. Okay, so the half filling would be the neutrality point. So we were interested in understanding the correlated electron physics here, but in order to do that, we wanted to go into the Wannier basis, and then because this happens very close to, or most likely exactly at the commensurate filling, we wanted to understand this from the strong coupling side. But before we do that, we wanted to build the Wannier states. And that turns out to be not entirely trivial. And so this entire talk will be essentially how to build such Wannier states so that then you can study the correlation effects. That's, of course, my motivation. But as I said, it is not entirely trivial how to do that. Okay, so what we did is the following. We started by imagining that the two monolayers are sitting exactly on top of each other, so you have a perfect AA stacking everywhere. And then we twist one of the layers relative to the other by a commensurate angle. Keeping this AA stacked site intact. So we have a twisted bilayer with the so-called AA registry. This introduces a new unit cell. For the magic angle, this would actually produce, this would give you about 10,000 or so atoms in a unit cell. But in principle, you just have a band structure problem. You can write a tie binding model on this and try to solve that, and then project onto the 4 narrow bands. Now, for this setup, this new crystal will have the so-called D3 symmetry, which is generated by a 3-fold rotation around the AA stack site. So that's marked here. As well as a 2-fold rotation about the axis that's perpendicular to the main rotation axis and goes halfway between the 2 monolayers, which we call C2 double prime. So you can imagine that if you were to perform 180-degree rotation about this, the blue will go into red and the red will go into blue. Okay, and now these two, in addition to translation, will generate your entire space group. Now, the commensurate structures can be labeled by 2 sets of integers, and the way to think about it is as follows. You see this point over here recovers the AA registry, and there are 2 different ways to get there. You can either follow the blue arrows, which are the monolayer unit cell vectors in real space, or you can get there in a different way. You can get there this way along the red lattice. This gives you the following equation for the 2 different integers. So in this case, A1 would be multiplied by 2, and A2 will be multiplied by 1. It gets swapped on the other side of the equation. But in any case, a pair of such integers, m and n, would then define the commensurate structure and the resulting twist angle. Okay, so now if you, this is taken from the paper by Moon and Coscino. If you look at the various patterns that you obtain by changing these integers to larger and larger values, you start obviously seeing the moire pattern. Now, the tie binding, microscopic tie binding model in this case was taken to be the following. There is a interlayer hopping within each monolayer that contains nearest neighbor, next nearest neighbor, etc. Terms with an exponential cutoff, as well as the intra-layer hopping. So you imagine you have a particular site, and then you look around this site, and within a particular exponential envelope, you allow a hopping to the next layer, and then these hopping amplitudes are calibrated by calculating the corresponding band structure in the case of LDA. You cannot do LDA calculation for realistic magic angles because there are simply too many carbon atoms, but you can do them for smaller values of the commensurate structure, and then you can calibrate these values, and then you can extrapolate to the point where the tie binding calculation can still be done, but the LDA calculation cannot. All right. So, so what we did is consider the following set of integers, 25 and 26, and this commensurate structure corresponds to a twist angle of 1.3. Now, that's not exactly the magic angle. The magic angle in the experiment is something like 1.1 or maybe 1.05. But the reason why we did not consider, and it would correspond to the set of integers 30 and 31, but the reason why we did not study that case is because in that case, as I mentioned, you see there's no band gap at the bottom of the band if you do not relax the structure. We were interested in describing the experimental setup in which you do see the band gap both above and below, and the closest commensurate structure that we found that does this is here. So we don't have 10,000 atoms per unit cell. We have something like 7,900 atoms per unit cell, close enough, but it does produce the desired band gap. Okay. So now let's see. So if you zoom in this particular D3 configuration at the bands at the gamma point, you discover that there is a double degeneracy here. It corresponds to a 2-dimensional representation of D3. One way to think about it is that each one of these block states at gamma can be chosen to be an eigenstate of this threefold rotation that I discussed, and its eigenvalue will be e to the I times 2 pi over 3, while its partner will receive the opposite phase winding. In addition to that, under the twofold rotational symmetry, the C2 prime that I mentioned, the axis that's perpendicular to C3 that's out of plane, the two states will go into each other. Okay, and a similar thing happens for the pair of states down here. On the other hand, if you were to zoom into the band structure at the K or K prime point, you discover that there is one two-dimensional representation, that's this, and then two one-dimensional representations. So, very good. So if you took the continuum model in which you do not allow valley mixing, of course the tie-binding model has the valley mixing built in, etc. What would happen is that this would close and you would get fourfold degeneracy here, and this would also be just twofold degenerate. In addition to that, this entire line between M and K prime would be perfectly doubly degenerate along the entire line in the Brillouin zone. Now, in a full microscopic calculation, that's never exact. There's always a little bit of a splitting along this line, and the structure at K prime point and the structure at the gamma point is just as I discussed. Now, in the continuum calculation, what you can do is you can separate out the two valleys. You can just turn off the intervalley mixing, and then what you would get is double degenerate for the single valley problem, double degeneracy at K, and then non-degenerate set of states at gamma. Okay, so now, all right. So just by looking at this, because this problem does not break time reversal symmetry, so it cannot have Chern numbers, and because your bands of interest are separated from the rest of the spectrum by a finite gap, you immediately know that you should be able to construct exponentially localized Wannier states. Now, I will discuss this in detail. There's no question in this field that such a thing can be done. The only question is, can you build such Wannier states in such a way that they respect the symmetries of the underlying lattice locally? Okay? And in that case, it is a valid question whether there is an obstruction to that. And I'll come back to this. Okay, so that's what we would like to do. We would like to build the corresponding Wannier states for these four bands. And as Luke nicely pointed out, if you were to plot the local density of states, for example, for the positive energy state, so this is entirely produced from the block wave function, you will discover that such local density of states is peaked at the triangular moire sites. Okay, so that naively suggests that the type of Wannier states that you would like to start with would be something that has a nice peak around the triangular site. And perhaps you would have some type of a type binding model in which you're hopping on a triangle lattice, and perhaps you have four orbitals centered around these triangular sites. Now that turns out to be incorrect, although there are some papers in literature which start with that. That's actually not correct. And one way to see that that cannot be right is to do the following. Imagine that indeed you do have Wannier states whose centers are at the triangular moire sites. Okay. Now also imagine that these states transform under point group operations that I mentioned locally. So what does this mean? Say you have this Wannier state labeled by I and the position of its center. R is a triangular moire lattice, and apply some symmetry operation G to this state. Well, because this represents the symmetry locally, you will obtain possibly a Wannier state at a different, centered at a different point, and in up to a unitary matrix. And this 4x4 unitary matrix will depend on which particular symmetry operation you have. Now, you know that you can construct block states from these Wannier states simply by superimposing them like this. And so now imagine that you have a block state at K, and you apply the same symmetry operation on this block state. You can just follow the algebra, and then you find out that the resulting block state will transform into a block state that's at different K point, up to a linear combination of the four block states, but the linear combination has to be the same as for these Wannier states. So once you pick your Wannier states, this matrix is you're locked to this matrix at any k point. Now imagine that this k point is the gamma point. Now you see the symmetry operation doesn't change the gamma point, and so that means that your block states have to transform the same way at the gamma point as your Wannier states do. Okay, well now imagine that this little k point is the corner of the Brillouin zone. That point also goes into itself under various symmetry operations, for example C3 and C2 prime. And so that tells you that the representations at gamma and k would have to be identical if you were to choose the Wannier state centers at the triangle moire lattice. But we already know from the analysis of the band structure and the corresponding block states that these representations are not identical. At the gamma point, you have two two-dimensional representations, and at the k point, you have one two-dimensional representation and two one-dimensional representations, which means that you cannot construct the you cannot have the Wannier centers at the triangle moire sites. A similar, although not the same argument, was provided in these two previous papers, one by Senthil and Ashwin Vishwanath collaboration, and the other one by Liang Fu and collaborator. All right, so on the other hand, you can construct Wannier states, which represent symmetries locally, which are centered on the honeycomb moire sites. So instead of being centered at these black dots, we claim that you can construct them in such a way that they are centered, these dual lattice, to the triangle lattice, namely the honeycomb lattice, so the red and the blue sites. And since we have 4 bands, we need 4 Wannier states. For us, 2 of them are placed on the on one honeycomb sublattice, and the other 2 are placed on the other honeycomb sublattice. All right. So how do you avoid this problem if you put them on honeycomb moire sites? Well, the way you avoid them is that avoid this problem is that now if you perform this rotation, you see some of these sites, they go into a different unit cell, and so in addition to the regular rotation of the triangle lattice, you receive this shift. Now, this shift actually changes the argument. If you follow the algebra, the block states will do this. And so now, you actually do not have to have the representations of the block states at gamma and k to be the same because of this additional phase factor that you pick up. All right. It also tells you that the representations at the gamma point, where this little k is equal to 0, are actually the same as the Wannier states, but at the corner of the Brillouin zone, they can be different. All right, so it's now very simple how to set up our Wannier states. We can start with block states at gamma to be eigenstates of the threefold rotation. And in this case, this matrix U has to be diagonal. And we can pick its first element to be 2 pi I over 3. That would fix how the first Wannier state of the 4 transforms under the threefold rotation. Now we can generate the second Wannier state on the same side, W2, simply by time reversal. You see, these states are not real because they are eigenstate of the threefold rotation with this non-trivial eigenvalue. Now, to get to the other pair of the Wannier states, we simply perform a twofold rotation around this dashed line, and that gives us, let's say, from W1, W3, and then finally, to get the fourth Wannier state, we time reversed W3. And this is now our set of 4 Wannier states. Now, how do we actually construct them? This is a plot of the amplitude square for 2 of the 4 block states at gamma, the one at positive, the one at the high energy, the one at the lower energy, but both with the same C3 eigenvalue, and they have this peculiar propeller-like structure. So now, just for orientation, the AA stacked sites, so the moire triangle lattice sites, are these blue dots here. Okay? All right. So now, how does one construct this? This is a well-known procedure. It's been discussed many times, but there's a beautiful review on this by Marzari, Vanderbilt, and collaborators. So let me just tell you loosely what it is that you're trying to do in order to make these Wannier functions localized, exponential localized. Of course, the Wannier functions are related to the block function simply by Fourier transform. And the usual problem in practice is that the block states that your computer spits out are not necessarily smooth functions of K. All right. So you would like to make these block states as smooth as possible. There's a procedure. Okay, since I have 5 minutes, I will not go through this procedure, but there's a very clever way to construct this mixture. Okay, so what we do, we take trial states, simply cuts of the block states centered around the honeycomb sites. We feed it into this procedure, and then we also apply maximal localization algorithm of Marzari and Vanderbilt, and here's what we obtain. So what I'm plotting for you are the absolute value square for the first Wannier functions. You can obtain the resulting ones by the symmetry operations I mentioned. So indeed, as was mentioned before, they cannot be entirely centered on a single site and be, well, they cannot be all centered and peak at the same site. Rather, they have this peculiar three-peak structure. So the black dots are the triangle lattice, and the honeycomb lattice are the centers of these triangles. So you see, this Wannier state is centered on the honeycomb lattice, but it has three peaks on the neighboring triangle lattice sites. It has a eigenvalue under threefold rotation that is 2 pi I over 3, so it's not trivial. And in addition to that, they come almost entirely from one or the other valley, although not perfectly. Okay, so just to repeat, this is how we construct them. Once you have W1, which is what I showed you, you can construct W2 by time reversal, W3 by the twofold rotation, and W4 by the time reversal symmetry of W4. Now, this is how it reproduces the band structure. As you can tell, it does pretty good job, and that's it. Okay, so now in the remaining 25 minutes, I'm going to tell you a little bit about how this is related to the obstruction that has been discussed in literature, maybe very quickly. Now, there's a claim, there's a following claim in the literature, which states that if you have a twofold rotational symmetry about the z-axis, followed by time reversal, and then in addition, if the valley quantum numbers are conserved, which is the content of this statement, that U1 valley symmetry is a good symmetry, then there's an obstruction to building symmetric, so first of all, exponentially localized and symmetric Wannier functions. So this is similar to the type of obstruction that you know exists in quantum Hall effect, except for it's less severe because the key adjective here is symmetric. Namely, it has to represent the crystalline time reversal symmetry and valley symmetries locally. And this argument has been put forward by Senthil and Vishwanath collaboration. Now, so according to this argument, what I have shown you should not be possible. Okay, so let me explain to you why it is that it doesn't violate this obstruction. Okay, I'm not going to tell you why this is, since I don't have time to explain to you how this argument goes through, but maybe I'm just going to show you that in the microscopic setup that we have, we actually do not have a twofold rotational symmetry about the axis perpendicular to C2 prime, which you would call C2 double prime. And it would be the product of these two, C2 prime times C2 double prime, that gives you C2. We do have time reversal symmetry, but we don't have this one. And therefore, this is not an exact symmetry of our problem. So that's one reason why we are avoiding this obstruction. And the second one is that because everything that we have is on a tight binding lattice, we do not have a valley symmetry that's exact, and that allows certain mixing terms which otherwise would be prohibited. Okay, so neither the valley symmetry nor this C2T are exact in this microscopic setup, and therefore there's no obstruction. Now, in practice, the valley polarization is actually pretty good. It's about 90% to 10%, but it's never perfect. Okay, so there is still a separation of scales that this gives you. All right, this could also be tied to the so-called obstruction in the two-dimensional topological insulators with an odd Z2 index that was discussed by this beautiful paper by Solyanov and Vanderbilt. And essentially the conclusion from this is very similar, namely that if you have a non-trivial 2D topological insulator, so you have a gap in the spectrum, but you would like to build exponentially localized Wannier states, well, because there are no Chern numbers, you know you can do this. But if you try to make them Kramer's pairs of each other, you discover that it's impossible. Okay? So the way they avoid the obstruction is by breaking locally the time reversal symmetry, but it is actually encoded globally in some non-local operators. Okay, again, I don't have time to discuss the quadratic band touching and how this is related to things, so let me just flash my conclusions. I presented a method for constructing the symmetry adapted and maximally localized Wannier functions that correspond to the 4 narrow bands. They have 3 peaks around the moire triangle lattice sites, but are centered on this dual honeycomb lattice. They form a non-trivial representation of the site symmetry group. Yeah, I told you about the relation of these Wannier functions to 2D topological insulators. We believe that this model provides a firm basis for any further study of many-body effects, which is ongoing right now. Okay, thank you for your attention.
Thank you very much, Oskar. Are there questions? Yes, Wei.
Just a very quick question. Actually, yeah, same time. You have these 3 major peaks in the result. What are their states in terms of rotation?
Right.
In 1 or 2 or 3?
It's a LZ1. So they have to transform the same way as the gamma point wave functions. So under C3, they receive 2 pi I over 3 phase.
But the total angle momentum is 1.
Well, the angular momentum is not well defined once you're on a lattice modulo 3. So the only thing that's precise is that it is an eigenstate of a 3-fold rotational symmetry with an eigenvalue e to the 2 pi I over 3. Which you can loosely think of as an angular momentum 1, but it's not quite precise because there's an additional valley structure. So they have a very fast envelope. Exactly. 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 Correct.
More questions? Okay, while you think, I ask a fast one. It's a more generic one. In the bilayers, you would have the Slonchevsky-Weiss-McClure model, which would consider many hoppings along many neighbors.
Yeah, exactly.
Has anyone done that?
Yeah, so that's what this tie-banding model is.
I see. Okay. So you were taking several hoppings into account.
Yeah. So let's see.
And how do they compare with all this gamma 1, gamma 2, gamma 4 that they had?
Yeah, so it's right here, right? So these are effectively your Slonchevsky Weiss-McClure amplitudes. And the way this was constructed is that you have the pi orbital hopping and the sigma orbital hopping, because now they're not exactly lined up.
Yes.
And as I said, you start by doing DFT on a small unit cell where you don't have to discuss this. And then you fit the DFT to this kind of tie-binding model. Okay, so you calibrate the tie-binding model in the regime where you can do DFT. And then for the large unit cell, small twist angle, you can't quite do DFT. Well, people have actually tried, and a single point takes 40 days to converge. A single K point takes 40 days to converge. But you can do tie-binding.
I see.
And that's what this is.
I see. Thank you. Any more question? Yes? Just a second, Gabe.
I guess I was going to ask the obvious question that follows. So following this procedure, can you also then essentially do some kind of Hybridsson-Schluter thing?
I'm sorry?
Can you then do some kind of a Hybridsson-Schluter procedure essentially to extract the many-body parameters like you?
Yeah, so that's what we are doing right now.
Yeah.
Despite what was mentioned in the previous talk, this is not quite a Hubbard model because of this 3-peak structure. Okay, so the dominant energy is actually a cluster charging energy. There are additional terms in the interaction. So it is not exactly a Hubbard model problem to be solved because of this. So this is projecting the Coulomb interaction onto the subspace of the 4 narrow bands.
Yes.
So could you tell us how big these terms are relative to each other?
Yeah, this is still work in progress. Yeah.
Okay, but they're big enough to. So how big are these? So in the work in progress, how big are these terms relative
Yeah,
to the
it's
T?
still a work in progress.
Okay. Any more question? Yes?
So you said that one of the guiding principles here is that the local Wannier function have the right symmetry of the lattice.
Yes.
And what do you think will be the worst consequence of not exactly obeying this condition? What is physically going to go wrong? Because obviously, if you're looking at four-ordered states like charge density wave, that has to be important. But if you're like thinking about multi-insulator and things like this, how significant is this?
Yeah, that's an excellent question. One way to think about this is as a gauge choice, right? So if you choose a different gauge, so for example, again, it goes back to simpler setup, although related, that I mentioned. Sorry, in the case of 2D topological insulators, right? So in this case, you can try to do something similar, and you discover you can't obey the time inverse symmetry locally. So if you construct one Wannier state, and let's say it is a complex wave function, you cannot just write down a tie binding model in which the other time inverse partner would have the same shape, but it would not be shifted, and let's say spin flipped. Okay, that cannot be done. So you're encoding the time inverse symmetry globally. So it's sort of hidden. And so if you solve the many-body problem, you're free to choose the many-body problem in any gauge you like. So you could pick this gauge if you like. But if time inverse symmetry was broken spontaneously, it would be kind of hard to detect it. So therefore, the preferred gauges would be those where the symmetry is implemented in the simplest way, locally. And therefore, if there is some symmetry breaking in the, let's say in your exact solution, you'll be able to tell right away. So I think that would be the most direct reason why you would prefer to do something like this.
So you're saying that if we don't have symmetry breaking, then we don't have to worry about this too much. Is that what you're saying?
Yes, but how would you know you don't have symmetry breaking when that symmetry is encoded globally?
No more questions? Okay, so then let's thank our speaker again and prepare to go to the bar, Brahma, with Brazilian music, no food, right? It's it's just snacks. There are little snacks, drinks, and music to feed your soul.
I think that way of putting anti-correlated disorder won't work. Which I told you, right? Just J1 minus J1 plus delta. Why? Okay, so if I put a J1 plus delta here, think of the next bracket. I need to kill off the random mass term on that bracket. Right? That will force me to put a J1 plus delta on this. You see what I'm saying?
So you mean if you shift by a half?
Yeah.
Yeah. I don't think it matters, right? Because what matters is as you pause plane,
Yeah.
right? This orders are on its out, right? And if you do what we discussed.